everyone, my name is Maryam Davari. I'm a PhD student at Queen's University, Canada, under the supervision of Dr. Zulkarnain. And today I'm going to present our paper, Classification-Based Anomaly Prediction in XACML Policies. So I start the presentation with some information about access control and access control policies. Then I will overview XACML and XACML policies. Then I will talk about our research contributions in this paper. And then I will present our XACML policy anomaly prediction approach. It has different parts. It has anomaly definition, clustering of rules, and policy learning procedure. Then I will talk about evaluation, experimental evaluation, and I will show some results. And then I will talk about the related work, and then I finish my presentation with conclusion and future work. So, different services and applications available on the internet, like video conferencing, remote printing, they need secure interaction and authorization requirements. So access control have been used to secure and control resource sharing in different applications like web services, grid system, and so on. So what is access control? So access control controls which user, so human, process, application, these are all users, have access to which protected resources like database files for performing which action, reading, writing, executing, under which environmental conditions like time, location, and so on. So different access control models have been proposed. So it starts by DAC, MAC, and they have different limitations, and then RBAC, role-based access control, was proposed, and for decades these access control models have been used. So, and then because of the distributed systems, so we need more dynamic policies. Because of that, ABAC, attribute-based access control, was proposed. So it specified who can access what information, from where, when, how, and many more flexibility. So, and XACML is a language that is used to specify ABAC policies. That is the focus of this work. So the contributions, so we have three main contributions. So the design and implementation of XACML policy anomaly prediction using classification techniques. So the anomaly, so we formalize different types of anomalies like redundancy, inconsistency, irrelevancy, and incompleteness for XACML policies. Then we find the correlation between different types of anomalies with role size, with role attributes. So XACML. So XACML is the extensible access control markup language. It actually is a general purpose access control policy language, but it has a sophisticated expressiveness, and it has a large number of policies. So and because of the large number of policy and sophisticated of XACML policies, the consequence and effect of developed policies are not obvious to policy administrators. So because of that, the chance of anomalies is high. On the other hand, there are not enough mechanisms or tools to analyze these large number of policies. So in a nutshell, XACML can have different parts. It has a role, it has a policy set, and attribute and functions. For example, role can have different parts: effect, boolean, condition, and target. And you see that the role in XACML has different parts like subject, resource, action, condition, and also effect. And also the subject can have subject attributes, resource also can have subject resource attribute, and so on. So because of the complexity of the XACML policy, we don't want to bring that complexity to the presentation. So I just show you some simple ABAC policies that have different parts like subject, resource, action, condition, effect. You see that, for example, the first role is that admin role is a content and the type is budget. The action is update and the condition is that the project of the subject and resource are the same and the permission is given. Okay, so the goal of this work is to try to find that anomalies in the policies, right? So we have an X is the policy or rules, and then we want to find out why in the binary classification is about normal or anomalous, and the multi-class classification can be different types of anomalies. Okay, in the next slide I will describe what is the anomaly, how we formalize it, and the rest of the approach. Okay, our approach have different parts. First, we need to define or formalize anomalies for XACML policies. First, we focus on redundancy. So redundancy anomaly indicates similarity among roles. So when attribute of two roles with the same identifier having intersecting value, so they are redundancy. So inconsistency means at least there are two rules in the policy set that conflict with each other. So inconsistency can be static or dynamic. So static inconsistency means that a situation when there are at least two rules in the policy set that conflict with each other. For example, one of them gives permission, another one denies the permission. So we also have a dynamic inconsistency. Dynamic inconsistency refers to the situation when an incoming access request triggers at least two rules with conflicting decisions. And irrelevancy means that a rule is never triggered by requester or by any access request. And the last one is incompleteness anomalies. So rules are incomplete when existing rules are unable to cover access requests. Okay, the first step, we formalize these 5 types of anomalies. After that, so we cluster the policy rules, right? Because we believe that anomalies inside similar rule, the rule with similarity is, the chance of anomalies in rule with similarity is much higher than the others. And also clustering provide that flexibility and scalability for analysis. So because of that, we cluster policy rules. So you see that in our clustering algorithm, we cluster based on user attributes, resource attribute, action, and condition, and we assign different weight. So in this work, we assume that the sum of all these weights should be 1, but it depends on application. For example, one application may focus more on user attributes, and increase the weight. Okay, after clustering policy rules, the third step is that we apply a policy modeling technique or policy analysis technique. In this step, we use the approach that we propose in another work, that it formalizes policies using tree structure. So after applying a policy anomaly analysis technique, so we try to find out anomalies for each policy rule in each cluster. So redundancy and static consistency are detected in each cluster, but dynamic inconsistency, irrelevancy, and incompleteness can be detected by evaluating incoming access requests. And also I want to mention that, so in XACML we have a policy set, rule sets. So all our analysis are done at the rule level. Okay, after preparing all those policies and labels, so we want to apply machine learning techniques. So we need to pre-process that rule, right? For example, what we do, we find out the missing attributes in the data set. So we handle continuous attributes or conditions or interval between rule components. And also because we want to apply machine learning, as I said, we need to have a balanced data set. We handle all those. So after pre-processing rules, so we apply different supervised classification techniques like a random forest, decision tree, naive Bayes, support vector machine, KNN, and majority voting. Because we use majority voting because I think we all know that there is no specific algorithm that we say, oh, you have this data set, this algorithm works for that. We don't have that kind of algorithm, so we need to try different types of algorithm to find out which one can provide better result for our data set. Okay, I talk about the proposed approach. Now I want to show you the evaluation part, but before that I need to build a data set, because as we know, there is no real data policy data set that is available online. So because of that, I have to build synthetic rule sets. So I built 18 synthetic rule sets based on the subject attribute expression and resource attribute expressions, and then I define mean and variance. For example, the 6 role sets are built based on means of subject attribute and resource attribute expressions of 3 and variance 1. Another 6 sets are built based on attribute expression 4, and another one built with means of attribute subject and resource attribute expression 5. And each of these rule sets has 6 data set, and then they have different sizes like 100, 1000, 2000, 3000, 4000, 5000, and then the attribute value are in the range of 1 to 100, and in total each role can have 20 attributes. So these are the results. So you see that So these are the average redundancy rule and static inconsistency. So here we show the number of redundancy and static inconsistency with respect to number of rule and also the means. So on average, there is a significant number of the anomalies, both redundancy and static inconsistency. It can also observe that they show almost similar behavior with respect to number of rule and means of attribute expressions. So these are our results for dynamic inconsistency rule, irrelevancy, and incompleteness. Here you see that the behavior of dynamic inconsistency is almost similar to the static inconsistencies, and the reason is about the number of dynamic inconsistencies is much higher than the static one, because the policy the system administrator cannot detect the dynamic inconsistency when he or she develops policies. So another one is about irrelevancy. So you see that the growth rate of irrelevancy increase with when the means of attribute expression increase. So similar to the redundancy, static inconsistency, and dynamic inconsistency, the average number of irrelevancy increases with the number of rule, and also this is the result of the incompleteness. You see that the average number of incompleteness decreases with the number of rules. So these are our other results. So here we just show the clustering time, the time for clustering, construction, analysis. These are 3 steps that I talk about, that we do it in our approach. You see that analysis time that we use the tree-based policy analysis approach takes more than the clustering and also the construction time. So after finding out all those correlation and understand the behavior of anomalies, so we apply different machine learning techniques. You see that we apply 5 types, and then we compute accuracy, precision, recall, and false positive rates. You see that for example, for RS6, all these metrics are above 70%. That is so promising. And we have a low false positive that show the classification based technique has a potential to detect those anomalies. Okay, and also these are analysis time for tree-based policy analysis. When we just apply tree-based policy analysis, when we apply 5 classifier and also majority voting, you see that the 5 classifier based policy analysis is more efficient in terms of analysis time. Okay, about the work that have been done in this area. So you see that policy analysis can have a different branches that we didn't cover in this paper, but we focus on anomaly analysis assessment. So anomaly assessment can some work have been done on RBAC, ABAC, XACML, and then so you see that various approaches have been investigated to address the problem of anomalies, but the issue is that some of them focus on specific, especially inconsistency and redundancy. But in this work, we focus on proposing an approach to detect and also to predict all the anomalies at the same time. And also they develop for different models like RBAC or about mechanism. So in conclusion, what we have done, a large number of XACML policy may increase the risk of anomalies in distributed system. So in this work, we propose anomaly prediction approach for XACML policy based on data classification techniques. Also, we propose a clustering algorithm to make the policy analysis scalable. We find out the correlation between the types of anomalies and then different metrics, and also the majority voting give us the accuracy, recall, precision of 80% and really low false positive. And also so in future work, we plan to find an appropriate number of attribute expression. As you remember that we use the mean of attribute expression of 3, 4, 5, but in future work, we plan to find an appropriate number for that attribute expression to minimize the number of anomalies. Thank you so much.
Hello everyone, my name is Bian Jingfei. I'm from University of Chinese Academy of Science and Institute of Information Engineering. I am very pleased to be here. My research is an evolutionary learning approach towards the open challenge of IoT device identification. So it is our outline for today's presentation. With the continuous development of the Internet of Things, massive devices emerge in the network, causing huge security threats. The foundation of protecting IoT devices and preventing malicious attacks is correct and effective device identification. Device identification based on traffic is one of the key technologies. It can passively monitor the traffic of network devices, analyze the traffic, and identify the brand, type, and other attribute information of the corresponding device. It is very suitable for network device identification under high concealment requirements. However, device identification technology based on traffic currently encounters an unavoidable challenge called the open world problem. In a real open environment, Network devices are usually in the process of dynamic change and continuous increases, which brings great difficulty to the device identification based on traffic analysis. As shown, once the device identification model that performers will in the library is deployed in a real open environment, it will fall into the dilemma of performance degradation. It is because the model did not take into account the complexity and the variability of the real environment at an early stage of design, ignoring the fact that new and unknown devices will continue to appear in the network, which causes the open world problem. Therefore, this model cannot cope with the dynamically increasing new classes of devices and can only wrongly classify them to several predefined classes. So, the classification performance will continue to decline over time. However, the research work on the open world problem is not in depth. Early device identification work based on traffic analysis mainly includes text-based, traffic feature-based, and deep learning-based methods, which have made good progress in identification accuracy. But these research works do not consider the open world problem. In 2021, Hu et al. Proposed a model based on the idea of out-of-distribution. They not only allow the model to identify the known devices, but also detect the unknown. However, this method cannot further identify unknown devices. To address the open world problem, our insight is that the fundamental solution should be to accept new devices, not reject them. Just as human beings always have the ability to continuously learn in new environments. As shown, we intend to propose a network device identification model that can continuously evolve in the life cycle and continuously identify new devices to adapt to network changes. We may not yet understand what are the difficulties of evolutionary learning. We first analyze two simple solutions. JOIT. JOIT stores all the training traffic data that has appeared in history, and every time a new text arrives, it uses all the data to retrieve a new model from scratch. However, this solution greatly wastes the storage and computing resources and even leads to privacy leakage. Another naive idea is fine-tune. Fine-tune uses the latest traffic data to fine-tune the previous model. However, this approach will lead to several catastrophic forgetting, because the model will focus too much on the new task. The performance of the old task will drop significantly. The both two ideas are extreme choices between high consumption and high performance, which are obviously infeasible, and also illustrate the main difficulty of model evolution: how to avoid catastrophic forgetting and achieve better performance while reducing the consumption of memory and computing resources. Incremental learning needs our expectations. We will use incremental learning technology to propose an evolutionary learning model suitable for IoT device identification. Following, we begin by describing our analysis and findings which underlie our design. The first key point is the feature representation of device traffic. Most IoT device identification methods replace all handcrafted features. But for evolutionary learning, it is impossible to expect current handcrafted features to be useful for modeling new device behaviors in the future. Therefore, it is necessary to design a traffic feature representation method that directly relies on the data itself rather than had the design. The second key point is the defense of traditional network architecture. For evolutionary learning, generative feature extractors are crucial. If the extractor features only serve the current task, when a new device arrives, the parameters of the extractor will be drastically modified to regain new features favorable for the new task, which will cause spaghetti. In addition, the linear classification levels can become unstable and uncontrolled during evolution learning. Moreover, when learning to identify new devices, it is necessary to adjust and increase the output units of the network structure, which is cumbersome and inconvenient. In summary, traditional task-centric feature extraction methods and layer of fully connected classification are detrimental to evolutionary learning. Third, interclasses confusion and inference. As shown, the figure presents our findings from experiments on IoT devices. The features of the well-trained device form respective distribution regions, as there is no overlap between the features of base classes. However, with the introduction of the new device, the features of the old device are confused and overlapped. We argue that the confusion between features of the old classes directly leads to catastrophic forgetting. We will explain later how to use machine learning to control the Internet class separation to reduce confusion and interference. We adopt a decoupled architecture for evolutionary learning, divided into representation and device inference. We design an automatic feature representation scheme for device traffic, which is data-centric. Following, for device inference, we make use of the nearest class mean classification strategy or the latent representation. The first step is pre-processing. We find that when a device provides services, it always produces the neutral sequences of TCP packets that are highly related to its services. In contrast, due to the connectionless nature of UDP protocol, the network behavior based on UDP is less distinguishable than TCP. Hence, we consider using the TP session as the basic unit to process traffic. We arrange all communications of a session in a vertical request-response sequence, forming a two-dimensional matrix. As shown in figure, we randomly sample 4 sessions of 6 devices from the public dataset and visualize them using grayscale math. It is found that behavioral patterns differ significantly between devices. The analysis at the beginning shows the limitations of traditional architectures. Autoencoders have strong feature representation capabilities, thus we obtain traditional architectures, and creativity employs a thick autoencoder to learn latent representations for devices. However, the autoencoder is not well compatible with traditional full connected classification labels, and autoencoders cannot perform classification tasks independently. Hence, we introduce machine learning into the representation of autoencoder to automatically achieve independent compact spatial distributions. Specifically, we combine ideas from autoencoding and machine learning to produce a compact, representative, and class separable embedding space. Following, for device inference, we properly make use of the nearest class main classification strategy. We first use an autoencoder to map the traffic data of all devices into the feature space and then obtain the main feature vector for each device. Finally, we assign class labels based on the smallest distance from the main vector in the feature space. We have designed a model architecture suitable for evolutionary learning. However, during continuous learning with new devices, it is also necessary to overcome the inevitable forgetting of old devices. To elevate the forgetting, first we use an exemplar manager to manage the most representative samples from old data for knowledge replay. Then we develop a less forgetting construct based on special knowledge distillation and impose control of the distribution distance between clusters to reduce interclasses interference. In the evolution stage, at each moment, the model of the previous stage is regarded as the teacher model, and the model of the current stage is regarded as the student model. The figure shows the continuous realization process of dynamic evolution. Our experiments are based on three public datasets. In order to perform a multi-stage evolutionary learning, we merge all datasets together and then integrate the ejected TCP session data into a large dataset containing 66 different classes for experiments. In the experiment, we aim to answer the following research questions. Question 1. How about the accuracy of our proposed method after multi-stage evolutionary learning? Question 2. How will do various methods perform in evolutionary learning for the anti-forgetting of old devices? And question 3. How do key parameters affect evolutionary learning in experiments? And how do we make trade-offs in performance, computational resources, and memory? We conduct comparative experiments with various state-of-the-art methods. Our method significantly outperforms state-of-the-art methods under diverse experiment settings. And we use the confusion matrix and XACML to compare and analyze the forgetting that occurs in the evolutionary learning process of various methods. The vertical axis represents the correct device type, and the horizontal axis represents the predicted device type. In construct, our method performance view of both old and new devices. The FE score of our method is 88.31%. Finally, we also discuss the effect of the spatial distance parameter and the number of examples for evolutionary learning. The results prove our finding and also show that the greater the spatial distance, and the larger the number of examples, the better the effect of evolutionary learning. However, we have to take into account that as the number of samples increases, so does the memory footprint. So ultimately, we have to strike the right balance between performance and memory. This work is devoted to solving the open-world problem of IoT device identification from the perspective of model evolution. We propose a novel evolutionary model which can continuously learn with new device traffic. In future work, we will study how to use the few-shot learning method to reduce the workload of manual annotation, thereby improving the efficiency of device identification. That's all. Thank you.
Hello, everyone, and thanks for having me today. My name is Ehsan, and I have recently received my PhD in computer science from the University of North Carolina, Charlotte. And I'm gladly going to present our paper entitled SecureBERT, a domain-specific language model for cybersecurity. AI in cybersecurity has gained a lot of attention in the last recent years for different critical tasks, such as intrusion detection, phishing and spam detection, threat prevention systems, and malicious behavior analytics. Companies and enterprises massively invest in using AI-based technologies to protect their information and infrastructures against cyber attack in a more effective, faster, and a cheaper way. In the past recent years, and by growing the popularity in the internet and social networks and enhancing the computing power, text analytic and the natural language processing have become a powerful cybersecurity tool for vulnerability analysis, risk measurements, defense planning, threat action extraction, and in general, cyber threat intelligence. In cybersecurity domain, security analysts process the different cybersecurity related text to identify and extract threat information in order to monitor, prevent, and mitigate the threats. For example, agencies such as MITRE and NVD invest millions of dollars each year on human expertise to analyze, categorize, prioritize, publish, and fix the disclosed to their textual descriptions and third-party reports. However, this manual processing is problematic, impractical, and also it is expensive and slow, since as the number of product grows, the number of vulnerabilities increases, and therefore it is critical to utilize an automated approach that is capable of identify the vulnerabilities and quickly delivering the defense measures. NLP has been widely employed to analyze of domains, including cybersecurity. Language models as a core component of the NLP plays a critical role in NLP applications that interpret the qualitative input text and transform it into quantitative representation. Language models mainly made in order to capture the most important text features from the sequence of words from a natural language and utilize it for different underlying tasks. In this paper, we introduce a new domain-specific language model for cybersecurity, which is able to capture the contextual and semantic representation of the cybersecurity text. This model is very important in cybersecurity community as it can be maintained and utilized to automate many cybersecurity related tasks in the future. Before diving into the details, let's answer a fundamental question, which is why language model and why it is important. In the text analytic tasks, it is always required to represent the input text with numeric values. The traditional way to do so is one-hot encoding that works based on word occurrence. Similar representation that work only based on the frequency of the words in the text cannot effectively capture the semantic relationships and the contextual understanding. Therefore, language models introduce a new form of text representation known as word embedding or embedding representation that is able to convert human language, present each word with a multidimensional vector that preserve all semantic and contextual attributes within the feature space in the text. On the other hand, many of the existing off-the-shelf language models, such as BERT, have been trained on general English, and so they are good at representing the regular English words, but not advanced language, such as cybersecurity. For example, some words such as ransomware, API, or exfiltrate might be very uncommon in general English, so they may have improper representation in general language models. Meanwhile, there have multiple meanings when appear in different language domains. For example, words like honeypot, virus, or handshake carry totally different meaning in cybersecurity when compared with the general English. Therefore, it is not be very fully functional to leverage existing models to represent cybersecurity text. In the meantime, there is no or very limited number of domain-specific models to be utilized for text analytic in a particular domains. So it motivates building such models in all the sensitive domains such as cybersecurity for better and more efficient text representation. BERT is the most recent state-of-the-art design for language modeling, which is a transformer-based neural network that has outperformed all the older language models for standard NLP tasks. Building a BERT model requires two steps: pre-training and the fine-tuning. In the pre-training stage, the model is trained on unlabeled data against two different pre-training tasks called mass language modeling or MLM and next sentence prediction or NSP. In fine-tuning step, the BERT model is launched with pre-trained parameters, and then all or part of the parameters get tuned and adjusted using labeled data for the downstream task. We don't go to the details of the BERT's properties in this presentation, but since it has significantly improved the state-of-the-art results of the common NLP task, we chose to build our domain-specific model on top of BERT. A variant of BERT, which is claimed to be a robustly optimized version of BERT with certain modification in the tokenizer and the network architecture, and ignored NSP task during pre-training, is called RoBERTa. RoBERTa extends BERT's MLM and uses much bigger mini-batches and learning rates during the pre-training. It changes important hyperparameter in BERT that helps to greatly improve the MLM and accordingly the overall performance in all standard fine-tuning tasks. As a result of the enhanced performance and demonstrated efficiency, we developed SecureBERT on top of the RoBERTa. In order to build the SecureBERT, we leverage the RoBERTa pre-trained model. Unlike the existing models in different domains, which only retrained or fine-tuned the off-the-shelf model with new data without any modification, we have conducted a couple of novel and effective tweaks to enhance the efficiency and to build a more robust model to better represent the cybersecurity text. To this end, we designed a 5-stage process as follows. First, as any language model requires, we collected and cleaned a large amount of cybersecurity-related textual data from the online resources using our web crawl tool. The pre-trained model's tokenizer is built upon the tokens that are frequent in general English and may not cover important cybersecurity tokens. So, leveraging the collected data, we built our own domain-specific tokenizer to cover the maximum number of in-domain tokens for better input encoding. In the next step, we modify the pre-trained weights to generate a new representation and to make the training process more efficient as we retrain a large model with a smaller corpus size. After these modifications, we train the model with different hyperparameter selections leveraging parallel GPU processing, and then we evaluate the model to show the performance utilizing the dataset we created using cybersecurity resources. So let's talk about some details of these steps in the next few chapters. To create the training dataset, we collected and cleaned more than 98,000 files containing cybersecurity text from a variety of online resources such as books, articles, research papers, news, blogs, security reports, and the videos. This ends up with 2.17 million documents with average size of 512 words for each, and the corpus size of about 1.1 billion words with 1.67 million vocabulary size. It's good to mention that the 512 words refers to the pre-trained input size of the language model. Typical tokenizer breaks the raw text into small chunks called tokens, where these tokens help in better understanding the context or developing the model for the natural language processing and representation. RoBERTa's tokenizer goes further and breaks the words into the most common words and then breaks the less common words into bytes, or let's call it subwords. This method, which is called byte per encoding or BPE, has been proven to be more effective in better encoding the text and also resolve the out of vocabulary problem that exists in word-based tokenization and leads to a smaller vocab size as it doesn't have to consider all existing words along with all type of words in the vocabulary. The RoBERTa's pre-trained tokenizer is built upon the general English corpora and therefore does not contain many cybersecurity related words and subwords, such as, for example, crack, vulnerability, DNS, phishing, and ransomware. So we train the tokenizer on the collected corpus to cover all these important cybersecurity tokens to encode the input for model training. The vocabulary size of the pre-trained model is 52,265 words, so we use the same size to make our own tokenizer. After building our tokenizer with the new corpus, our investigation shows that there are 32,592 mutual words between the general English and the cybersecurity language, which means the cybersecurity specific tokenizer contains 17,673 new tokens that have never seen in the off-the-shelf one. Pre-trained models typically return the embedding representations of the tokens, where these representations preserve the semantic and contextual meaning of the tokens according to the corpus that it has been trained on, which is a general English corpus in our case. In this context, some words such as email, internet, and computer have the same meaning in both general and cybersecurity language, while there are homographs, which are the other type of words that may have different meaning in different domains. For example, words like virus, worm, honeypot, and patch have the different meaning in cybersecurity when compared to the general English language. Here, the objective is to somehow modify the weights for these words during training to make the embedding to return the correct vector representation. When a neural network is trained on a small dataset, it may memorize all training samples, resulting in overfitting and poor performance in evaluation. In addition, due to the unbalanced or sparse sampling of points in the high-dimensional input space, small datasets may also pose a more difficult mapping task for neural networks to tackle. This applies when one tries to perform continual learning, similar to what we aim to do in retraining the Roberta to create SecureBERT. The pre-trained model has been trained on billions of records on general English, and the weights for the tokens have been learned robustly based on that corpus. Continual learning on these adjusted weights might be expensive or may lead to overfitting if overtrained with many iterations. To resolve this issue, we add a small noise to the pre-trained weights to generate a secondary representation for each word in the same space. The idea is, if the word has the similar meaning in the new domain, the vector representation would match the original weights. Otherwise, it will deviate more and establish a totally new representation in the new space. To this end, we take each embedding representation and add a small Gaussian noise to each one and replace the new weights in the model for the training. Finally, we train the SecureBERT using 8 Tesla V100 GPUs running parallelly for 250,000 steps for 100 hours with the batch size of 18, using Hugging Face framework with Atom Optimizer and cross entropy loss function against masked language modeling, or MLM. To recall, in MLM, the model dynamically masks 15% of the words in each input randomly and calculate the error for predicting the masked words at each iteration. We evaluated the SecureBERT for both pre-training and fine-tuning model. In pre-training, we aim at evaluating the performance of the model in predicting the masked words in the input. As there is no such dataset containing masked cybersecurity words, we manually created a dataset of more than 17,000 sentences extracted from MITRE ATT&CK technique and tactic records. We divided these sentences into two parts. The first portion contains about 12,721 sentences in which one cybersecurity noun is masked, and the second part comprises 4,620 sentences with the masked verb. We use SecureBERT and 3 other models, including Roberta Base, Roberta Large, which is a much larger model compared to Roberta Base trained on a much larger corpus, and another domain-specific language model called called CyberBERT, which is trained on biomedical and computer science research articles. Our cumulative accuracy results shows that SecureBERT significantly outperforms other models in predicting cybersecurity mask words, showing its great potential in understanding and representing cybersecurity implications before even it is fine-tuned for a specific task. Here are some examples of predicting mask words using SecureBERT. For example, the word reconnaissance is masked in the information from these scans may reveal opportunities for other forms of mask word, establishing operational resources or initial access. SecureBERT correctly predicted this word, while Roberta Large, despite its large size and good performance in general English, predicts the mask word as early, which is not necessarily a correct output for this example. In other example, words such as hijacking and DDoS, which refer to the core concept of the other two examples, are incorrectly predicted by Roberta Large, while the SecureBERT did a great job in capturing the semantic relationships and returning the correct words. As mentioned earlier, we have conducted two modifications such as creating a new tokenizer and also modifying the pre-trained weights. To show the effectiveness of the new tokenizer, we compared the performance of the two versions of the SecureBERT on masked language modeling, one with Cybersecurity tokenizer and the other which is trained using the pre-trained general English tokenizer. Our results shows that the version with Cybersecurity tokenizer performed better than the model with pre-trained tokenizer, indicating the effectiveness of using the domain-specific tokenizer for training the SecureBERT. Pre-trained weight modification helps in more efficient learning in training the SecureBERT. This table shows some examples that how it affects the training and accordingly the output when tested on MLM task. Suppose the word virus is masked in a simple sentence such as virus causes the masked word. Virus is a term which has different implications in general and cybersecurity language. It may refer to tiny species which cause disease or may mean a piece of code used for cyber attacks. A powerful language model can easily detect the contextual meaning of this word within the given sentence and figure out the masked word can be something like DOS or denial of service, crash, or reboot, which makes sense in cybersecurity domain. And we see this happens in SecureBERT output shown by SB abbreviation. This meaning implication, however, cannot be detected by general English models, and they may return some words referring to viruses' general meanings such as cancer, infection, and autism. In the meantime, if the SecureBERT is trained without initial weight modification with the same number of training iteration, it returns some words in between, such as problems or disaster, which shows the model may require more number of training iterations to adjust well and return more legit words for the masked tokens. Similar examples for honeypot, worm, firewall, and zombie, and many other can make this assumption correct and therefore confirm the importance of the weight modification in training the SecureBERT. As mentioned earlier, there are limited number of datasets to evaluate cybersecurity language models. MalwareTextDB is a dataset containing 39 annotated APT reports that comprises 6819 sentences that action, subject, object, and the modified have been annotated in each one. We fine-tuned the SecureBERT along with pre-trained Roberta and CyberBERT for name entity recognition task on this dataset as a downstreaming task. Despite the fact that this dataset does not necessarily annotate the cybersecurity related entities, the SecureBERT slightly outperforms other models in this task in predicting the correct entity among each sentence. In this paper, we introduced SecureBERT as the first domain-specific language model that is purely trained on cybersecurity corpus and evaluated on number of standard NLP tasks. This model shows a high performance in all tasks when compared to the other models that makes it a reliable model for vulnerability classification, threat extraction, entity recognition, and many other important cybersecurity related tasks.